Welcome back to another video, and in this video we're going to be asking ourselves, how can we manipulate the function f of x, right, or any other function that we have like g of x or h of x, into something that can change the position of where the function is, right? So as in previous subjects, for example in geometry, we learned about translations on the x-axis, on the y-axis, and also reflections and making it larger or appear smaller, right? Well, it goes the same way as how we usually do it with functions. So what we're going to be explaining first is reflection. So now, during reflection, it works really similar with shapes and objects. So there's something about reflecting it on the x-axis and reflecting it on the y-axis. Now, let's say that we have a given function named f of x, right? We have a given function of f of x. Now, how can we first off make f of x reflect over the x-axis? And how do we make it reflect over the y-axis? Now, that's a very good question. So when we're reflecting it over the x-axis, we want to make it so that the whole entire function is negative, right? So basically we're just like making it somehow reflected over the x-axis by making it by a negative function. So we can write down negative f of x. And let's say we want to reflect it over the y-axis, right? Then that would be f of negative x, right? And we're going to use some graphs to show this representation that we have here. All right, so here I have 3 of the graphs, right? And we're basically using this graph of f of x, right? And we're basically reflecting it over the x-axis first. So let's take a look. When we reflect it, let's say this is the first graph that we have, right? F of x. Now, let's say that we're reflecting it over the x-axis, right? So now we're making this portion that's currently positive, right? From all the way from here, all the way to infinity, right? We're gonna reflect this singular part over on the x-axis. So then it would look something like this. I'm gonna draw this in blue. It's gonna look like this, right? And now for our second part, right, we're gonna name this number 1. And for our second part, which is on the negative area, from negative infinity to 0, we're gonna reflect that over the x-axis as well. So then, since we're reflecting that over the x-axis, the points that would only change, right, is gonna be the y value, right? So then it would look something like this. And that is what is clearly shown here in our second graph, right? Now this is the reflection over the x-axis, which we can call it negative f of x. Now, this third graph that we have here, all the way on the right, is just when we overlap the 2 graphs together. So this is an overlapping of f of x and negative f of x. So that's the original function and the function where we reflected over the x-axis. Now, it's a little bit hard to understand, but as I put it into simpler terms here, right, it's going to be a lot easier to understand. So when we're trying to reflect something over the x-axis, right, the variable that isn't changing, that is not changing, is the x component, right? So like let's say x equals 1, right? It's still going to be equal to 1, right? But then the values that are changing is the y. Because let's say you have, I'm gonna scroll down here. Let's say you have a graph, right? This is our little graph. And we're gonna be relating this to geometry by a little bit. Let's say you have a box here, right? And you're trying to reflect it over the x-axis, right? Now, just because we're reflecting it over the x-axis, then the new box would look something like this, right? And you see how the points here with the x-axis always lines up somehow, right? So now that's telling us, hey, when we're reflecting over the x-axis, the x doesn't change. The x values don't change. So that means that the y values has to change. Therefore, why we also say that, hey, when you're reflecting over the x-axis, the function as a whole becomes negative, right? So let's say this box was originally f of x, right? Now it becomes negative f of x. Another way that you can think of this is thinking that using a basic formula, right? So when we say f of x, right, we're just saying that x as an input, right, of the function. And what we really understand is that f of x is just y, right? And in this case, y is changing. So if we want to change y, we have to change what y is. And using the base formula of y equals mx plus b, as you probably remember from Algebra 1, this y here can change whatever is here, right? So y is the output, x is the input. We're just changing the output so that it's reflected over the x-axis, even though we do not want x to change, right? X has no change here. Now, we're going to explain the same thing over with when reflecting over the y-axis, right? Let's see. Reflecting over the y-axis. Now, when we're reflecting over the y-axis, right, the symbol that we want to change is going to be negative x. I mean, we're going to change the x value, right? So what is changing is the x value. Now, what is staying the same, right? Staying the same is your y values. Just like how we explained it about reflecting over the x-axis, where when you're reflecting over the x-axis, the x value don't change, but the y value changes. It's the complete opposite here when you're reflecting over the y-axis. So let's say you have our makeshift box again, right? Now, our box is right there. Now, when we're reflecting it over the y-axis, think about y as the mirror, right? It's like you're going to the mirror yourself and you're looking at yourself. It's basically a reflection of you, right? So when we're reflecting this box over the y-axis, right, the box is going to appear here. Now, what is negative, right? What just became negative here? Now, you might tell me, oh, the x value changed, right? The x value changed to negative, right? So how can we represent that inside of our function, right? Our original function is f of x. Original function. And then after the change, since our x value is turning negative if it was originally positive, right? Then we will write f of negative x instead. Now remember, this f of negative x doesn't mean that the whole entire function is changing negative, right? It just means that the x value is changing negative. So let's say we have f of x equals 5x plus 2, right? When we reflect it over the y-axis, it's going to turn into f of negative x, right? So then that would just be equal to negative 5x plus 2, right? The y is still the same, but the x changed from a positive to a negative, right? This is the same case as it is with the reflecting over the x-axis, right? As we review what reflecting over the x-axis was, let's say the equation for the x-axis was y equals 5, well, f of x, right? F of x is equal to 5x plus 2. We're going to use the same equation down there. Now, just because we're trying to reflect it over the x-axis, we have to make the whole entire function negative, right? So we're going to add a negative symbol in the beginning of the function. So it'd be negative f of x instead of f of negative x, right? Now, since we're taking the negative of the whole entire function, we have to distribute the negative symbol to all of the terms inside of the function. In this case, we only have two terms. So negative, and remember about the parentheses, 5x plus 2, right? And at the end, that'll just equal to negative 5x minus 2, right? An easy way how we can see that, hey, the y axis change, right? The y-intercept change is because we have it perfectly in the mx plus b form. And this last term here, I'm going to box this in red. This last term tells us what our y-intercept is. In this case, it turned from a positive 2 to a negative 2. So that means that the y changed. Now let's go back to the previous example that we just did with reflecting over the y-axis, right? We see that the original was plus 2 as our y-intercept, and after the change is still plus 2. So that means that the y did not change. So now let's do some practice problems with reflection over the x and y axis here. So let's say that f of x, is equal to x squared plus 6x plus 5. Now, 1, reflect over the x-axis, and of course 2, reflect over the y-axis. Now pause the video here and see if you can figure this out. Hopefully you just took a moment and figured this out by yourselves. So whenever we're reflecting over the x-axis, we said that the x doesn't change, right? So we want to change what the output of the function is. So then it'll be negative f of x, right? And negative f of x is just equal to negative of x squared plus 6x plus 5. Remember, always put your parentheses if you're going to do this way, right? Because then later on, you want to distribute the negative to all of the terms inside of this function, right? So now our function reflected over the x-axis will just be negative x squared minus 6x minus 5. And for reflecting over the y-axis, we said that the y won't change, right? The y values won't change. So that means that the x values has to change. So in that case, we want it to set equal to f of negative x, right? And when we have negative x, this will just be equal to negative x squared, right? Plus 6 times the negative x, and plus a 5 at the end, which is simplified to x squared minus 6x plus 5. Now it's that simple with reflecting over the x and y axis here. So as a review, whenever we're reflecting over the x-axis, it's always going to be negative f of x, the negative function, right? But if we're reflecting over the y-axis, we have to set the x to a negative, right? So instead of x, we're going to have negative x. So it would be f of negative x, all right? Now, previously, in the beginning, we mentioned a little bit about making things larger and making these things smaller. That is what we call something called distortion, right? Distortion. Now, this is something that you're going to learn more when you learn about like waves and trigonometric functions, because it mainly fits really well in there. But right now I'm gonna teach it to you and see if you can understand it. So now, when we're having distortion, things can shrink or they can stretch, right? And the thing is with these shrinking and stretching, right? We have to find a way how to match it onto the function itself, right? And the thing is, since we have a y component, we have a y-axis and an x-axis, we're going to assume that we're going to have to deal with vertical shrink or stretch and then horizontal shrink or stretch. So let's first talk about how things would change vertically, right? So vertical shrink or stretch. Now, the way how we would basically tell if there's a vertical shrink or stretch is if, let's say, a coefficient, right? There's a coefficient of the function, right? So it could be a of f of x, right? In this case, a is just a number. Now, it's like you're multiplying a certain value to that function so that it gets larger or smaller, right? So if it was like a fraction, of course it would get smaller because you're basically multiplying the f of x by how much times to make up the size for it. Let's say you have a box, right? A cardboard box, and you want it to have 2 times as large, right? So then you would just do 2 times the box, right? To make it 2 times larger. But if you want it like 2 times smaller, then you have to make it into a half, right? If that makes sense that way. Now, the reason why I've said that it works well with the trigonometric functions, with waves and everything, is that it shows a lot about it. So we have things called like amplitudes and periods. Those are going to be later on. This time it's just going to be like an introductory where we have all of these waves. So let me pull up the waves graphs and then we can take a look. All right, so we're here back with the graphs, and what we can tell is that this is the original graph here. So scroll down a little bit, all the way. This is our first graph here. Let's name this f of x, right? And then this is 2f of x, right? So now let's take a look. Our highest point on this graph is just 2 here, and our lowest point is negative 2, right? So we can say that for this graph, our range, remember from last video we talked about range is from negative 2, comma 2. Now, for our original graph, our topmost part is just 1, and then our bottom part is just negative 1, right? So now we know that our range here is -1, 1. Now, you're going to ask me, why does this even matter in the first place, right? So remember how we said that this was primarily for vertical shrink or stretch? Shrink or stretch. Now, we're basically taking this function, right? It has all the same x values for like the points and stuff, like the zeros, and it has everything's the same, right? Just that we're manipulating the function so that it's being stretched vertically, right? So if we did the reverse, and if it was like 1/2 f of x, right, then yes, it would shrink much smaller. But in this case, since we have the a value, right, in the base equation of a times f of x, just because the a value is larger than 0, larger than 1, then it must be growing larger. If it's less than 1, then it's growing smaller. So we can write that rule down here. If a is larger than 1, then it's stretching, right? And then if a is smaller than 1, then it's shrinking. And of course, if a is equal to 1, that just means no change, right? Now, this is why I said that this makes sense with a trigonometric graph, right? These things, they will shrink or stretch based off of what you do to the equation, right? What I've seen is that they've told you to manipulate the equations so that you can basically stretch the graph horizontally or vertically, right? Now, how would we be able to represent a horizontal shrink or stretch with these kind of graphs though, right? So let's write down horizontal shrink slash stretch. Horizontal shrink slash stretch. Now, the whole point that how we're going to find this out is just by f of b of x. F of b times x, right? Now we have a factor here, right? It's multiplied to x. Now, of course, we're going to have the same deal with like, oh, if it's larger than 1, if it's smaller than 1, right? Things are going to change around here. So let me pull up the graph as a representation so that we can check it out. All right, so now this is what you have to be careful of. So things kind of like, they're the opposite basically. So remember how we've said that for the vertical, right? If a is larger than 1, then it basically stretches, right? And then if a was less than 1, it shrinks. But in this case, if b is greater than 1, it shrinks. And then if b is smaller than 1, it stretches. And of course, if b is just equal to 1, then there's no change at all. Now, these are our graphs here, right? So f of x is our first graph, and the second graph is just f of 2x. You see how since our b is much larger than 1, it kind of just shrunk horizontally, right? In this is, remember, this is the same domain, right? We see like one hill right here, and then we see another hill, right? But in this case, we see 1, 2, 3, 4. We see 4 hills here, right? So of course, it's gonna multiply how much hills there are by 2 times. Okay? Now, of course, this would be similar to what we've seen in a polynomial graph, right? Now, remember, these rules only apply for trigonometric functions because they're a little bit more special on a case, right? So now, the way how polynomial graphs work, right? they work a little bit differently. So like if you have x squared or something like that, right? So that is what we're going to be talking about next. What if for whatever reason we don't have a trigonometric graph, right? And we have instead of x squared. So let's say f of x is equal to x squared, right? Now, let's say that this graph is 2f of x, right? And then we're going to draw another graph that says f of 2x. And of course, we all know what a x squared graph is, right? We have this. So an x squared graph is just like a u, right? So that's what it is. Now, the main reason how we can think of this is just by a table of values, right? So for originally an x squared graph, we can have like values of 0, 1, 2, right? Then that'll just be 0, 1, and 4 for the y, right? But let's say it was 2f of x, right? 2 times f of x. Now, that would be a vertical shrink or stretch, right? So let's take a look. If we have the xy here, right? We're going to use the same values, 0, 1, 2, right? Now, how would we figure this out, right? So now, if 0 was x, then of course it's going to be 0. If 1 was x, right? So now f of x, in this case, would be equal to x squared over 2, because you have this 2 in the front, and to make f of x singular so that it becomes like the y equals mxb plus y equals mx plus b form, you have to divide that 2 on both sides, right? And so that'll be 1/2. And then of course, if it was 2, then it'll just be 2, right? Because 4 divided by 2 equals 2. And so by taking a look at these values here, right, we can tell that the y value, the y components has actually shrinked by half the value, right? Let's take a look at the horizontal shrink or stretch, right? Here we have the horizontal, 0, 1, 2, right? So now let's take a look at this case, right? When x equals 0, of course it's going to be equals to 0, right? When x equals 1, it's going to be f of 2 instead, right? And f of 2 equals to 4. And then if it was 2, then it would just be f of 2 times 2, 4, right? So that's f of 4, which is equal to 16. Now, over here, instead, we see it's horizontally shrinking, right? Because the values are getting larger and things are happening here. So let's use a graph representation, because using the table representation is kind of hard to understand. So we're going to pull out the graphs and see. Alright, so here I have pulled up the graphs of f of x equals x squared. Here we have f of x equals x squared. Now for a second graph here, we have 2f of x. And then for our last one, we have f of 2x, right? So now, just by taking a look at this, right, we can tell by relating it back to our primary function, our original function, which is f of x equals x squared, right? And for our 2 times f of x, it looks like it became vertically like stretched, right? So we can say that there's a vertical stretch here. Now for our f of 2x, right, we can say that it horizontally shrank. Horizontally shrunk. Because now here's the explanation here. Since we know that the 2 is in the front, right, we know that this is going to be something about the vertical component, right? And just because it became a lot skinnier right here, right, so that means that everything had to stretch up, right? So that's how we basically find this out. Now on this one, on the last one that we have here, the 2 is in front of the x this time, right? So now since the 2 is in front of the x this time, which we know that, hey, it's going to be something going on with the horizontal, it's basically shrinking inwards, right? Or basically becoming more skinny at this point, right? So that's how we try to figure out and understand this. Now, our last part for today is going to be how can we shift things around, right? So that's something what we call translation. Now, translation is a really big topic that many people ask about. Translation. Now, translation is the same thing as how we would translate like objects and geometry on the graphs, right? So let's first start off with vertical shifting, right? Vertical shifting. Now, if we're vertically shifting the whole thing, right, it's either going to go up or it's going to go down, right? So we know that it's or up or down motion. Now, how can we actually tell by how it shifts, right? So we have something called a y-intercept, and from the y equals mx plus b form for an equation, we know that the b is the y-intercept, right? So by deriving it from that, we can tell that, hey, if f of x plus some number k, right, this will shift it up and down. Because it's just the value added to the original y-intercept, right? So let's say that f of x is equal to mx plus b, right? Say f of x equals mx plus b, then, right, in this case, f of x plus b, f of x plus k is just going to be equal to mx plus b plus k, right? Now, these two, remember, those are numbers, right? Those are like integers or random numbers that we have here. And when we add those together, it forms a new y-intercept, right? So that's how we know if a graph is shifting up or down. Now, there's a rule with this, right? So if k is greater than 0, then the graph shifts up k units, right? So let's say k in this case was like 5, right? So now we're shifting up the function 5 units, right? So let's say that k is less than 0. What happens if k is less than 0? Now you might have guessed it, the graph shifts down by k units. Alright, so let's look at an example real quick. So let's say that f of x plus 3, right? Is this shifting up or down? Shifting up or down, and also is this how much units is it shifting? Units of shift, right? And then let's give you another example. F of x minus 5. Shifting in what motion? And then units of shift. Now take a moment to yourselves and see if you can solve this right here. Alright, so hopefully you just paused the video and looked at it. And since we have a positive instead here, right? So we know that it has to be shifting up, right? And since we see it's plus 3, so that means that it must be shifting up by 3 units. It's not that complicated. It's very straightforward. You can tell it by whatever function that you have here. So in the second case, oh wait, it's negative, right? So we must know that it's shifting downwards. And now, since the value is 5, we know that it's shifting downwards by 5 units. So now, how would we know if there is a horizontal translation, right? So when we say that there's a horizontal translation, we meant by like horizontal, shifting it left or right, right? So horizontal translation. Horizontal translation. So what we're moving, right? We're shifting left and right. Left or right. Now, how can we actually tell if it was shifting left or is it shifting to the right, right? So now this gets a little bit complicated. Now, the whole point how we would find it, right, would be f of x minus h. Now remember, h is just a random number, right? So it could be like 5, it could be 6, it could be -5, right? And all of this basically adds up together, right? And by what we can tell is that whenever we have a shift going on, right? And with that shift, we need to know if it's going to the left or is it going to the right, right? And it's mainly like more thorough when we talk about the zeros of a function, right? So if for whatever reason we have a function, right? And h in this case is negative, right? Now we have a negative h, so then the negatives would cancel out and it would become a positive, right? So here we go. We have the rules again, right? So if h is greater than 0, then it's shifting to the right. Shifting to the right. Now, if h was smaller than 0, it's going to be shifting to the left. Now, don't get this mixed up with how it's being said, right? You must remember that there is always that negative in front of that h. In all cases, it's going to be negative in front of that h, right? So you must remember that since there's a negative, right? Even though it might say f of x plus 5, right? You have to really know that h in this case, right, is just equal to -5, right? Because it's the same thing as f of x minus a -5, right? Because x minus a -5 is the same thing as x plus 5, right? So you must remember that there is a negative symbol in front of that h, because that's what people mess up on a lot. They forget about the negative and then they think that, oh, it's the complete opposite, right? So let's take a look at some examples here. So let's say that f of x plus 3, right? So it's this shift where, what motion is shifting in, and also by how much units. And then you have f of x minus 5, shifting how much units? I mean, shifting what is motion, and then shifting by how much units here. So take a moment, pause the video here, and see if you can figure this out. Now, hopefully you just took a look at these problems and see if you can figure this out. So we're gonna write down the base equation on the right here, just to let us know that, hey, this is the base equation, right? So the base equation is f of x minus h, right? So in this case, if we put f of x minus h here, right? How much units? It should be -3, right? H is equal to -3 in this case. Because it becomes the same thing as f of x minus a -3. And we all know that it becomes positive here, right? So that positive matches with whatever positive we have here. So now since h is equal to -3, it's less than 0, right? So that means that we are shifting to the left, right? And based off of how much units we have, right, since the value is 3 here, we know that we're shifting 3 units, right? And for this last one we have here, we see a 5, right? We can definitely tell that, hey, we're shifting 5 units. Now we gotta figure out, oh, are we shifting it to the left or are we shifting it to the right? Now, using the base equation of f of x minus h, we see that the negative signs match up. Hey, very good. So that means that h is equal to a positive 5 instead, right? So we know that we're shifting to the right. Now, a way that I would look at it, and it would make complete sense to me, is by thinking about it without the negative symbol, right? Whenever you don't have the negative symbol, the rules, they reverse, right? So it depends on if you want to think about it the original way, where it's f of x minus h, or if you want to think about it the f of x plus h, right? So now I'm going to introduce to you what I would do in these type of scenarios. So we know we have f of x minus h, right? Where h is less than 0, then it's shift left, right? And if h is greater than 0, it's going to be shift right. Now, a way that I would think of this is just like this, f of x plus h, right? Now, here's it gets a little bit tricky. Because just because you just change one of the symbols here, right? It's going to change whatever boundaries you have. So then in this case, it would just become, when h is less than 0, it's shift right. And then if it was h is greater than 0, then it's shift left. You see how these two different ways could be different? Like, they can have the different operators, right? They can have different, like, symbols and whatever. But at the end, you still get the same thing that you wanted to get, right? So relating back to the problems that we just did with the positive and negative, right? So if we think about this in a positive way, right, using the method that I just told you, then we can tell that, hey, since it's a positive 3, it's shifting to the left, right? It's complete opposite, right? So now, these two here are opposite of each other. Just because we have this sign change, and these are also opposite as well, right? Just because this is opposite signs, the statements that we have, the conditional statements, right, are also opposite of each other now. So that is also a different way to think about it. So now remember that we've went over translations, we went over reflections, and also we went over making them stretch or shrink, right? So now, rotation-wise, rotating something would be a completely different thing, because that would involve inverse functions, right? So that's going to be a different topic, a different day. So in this video, we just learned how to translate functions, how to reflect functions over the x-axis and the y-axis, and also how to stretch them vertically or horizontally, or we can also shrink them vertically and horizontally. So remember to keep on practicing, and also I'll see you guys in the next video.